Good afternoon, everyone. Today we're going to finish off chapter 3. This section is on graphing rational equations. And this is for college algebra at College of the Sequoias. And this is section 3.5. Section 3.5 is on graphing rational equations. In 3.4, we learned how to graph general polynomials. But graphing rational equations is a little bit more challenging because rational equations, if you recall, have variables in the denominator. We can have a function of x on top with a function of x on bottom. And the only real requirement we have is q of x, the denominator, cannot equal 0. So let's look at the most basic one there is, the reciprocal function. The reciprocal function is f of x equals 1 over x, or y equals 1 over x. So the denominator can't equal 0. This indicates to us x cannot equal 0. And notice the numerator equals 1, which means it never equals 0. Which means y never equals 0. So we end up with another problem. Y cannot equal 0. There's just no way to get it in y equals 1 over x. So let's take a look at what's happening in Canvas. Not Canvas, Desmos. Should have had this on top. Y equals 1 divided by x. Okay. Notice that doesn't matter how close as we zoom in, as we get near the y-axis is where x equals 0. The graph never crosses it. And when we get near the x-axis, where y equals 0, it gets close to it, but it never crosses it. When a graph gets close to a line but never crosses it, we call that line an asymptote. So an asymptote is an invisible boundary that isn't crossed by our graph. With very few exceptions. And we'll discuss the exceptions in a little bit. The way we graph an asymptote is we actually use a dotted line, a dashed line. So let's see if I can actually do that here. X equals 0, and I can make this line, and y equals 0. I want to go to the settings, and I want to make these dashed lines. They don't show up very well. I wonder if making them dotted lines will make them look better. There they go. That looks better. So these asymptotes don't get crossed. And we can look at what happens for a couple values of x. So we got y equals 1 over x. We know x can't equal 0 and y can't equal 0, but we can do other values. Like let's do -2, -1, -1/2, and maybe 1/2, 1, and 2. The reciprocal function just flips these over. -1 flipped over is still -1. So we have an asymptote right here. And we have an asymptote along the y-axis. And we have points at 1, 1 and -1, -1. We have -2, -1/2, and -1/2, -2. 1/2 and 2, 2 and 1/2. And does this kind of thing. What happens if we have a bigger denominator? What happens if we look at y = x²? Or 1/x²? Let's make it red. We still have asymptotes. X can equal 0, y can equal 0. But notice how the graph changes. When we're less than 1 in the 0 to 1 region, it's taking longer to get near the x-axis or the y-axis. When we're greater than 1, it's getting near the y-axis faster, at least when we're in the positive region. In the negative region, what happens? Well, y = x², when we have a negative number and we square it, it makes it positive. So it flipped the graph upwards. So there's like an infinite spike at 0. What happens if I make this a cube? And now the same thing happened for values greater than 1. It gets close to the x-axis really quickly. Values less than -1, it's getting close to the x-axis really quickly. But between -1 and 1, it's taking longer to get near the y-axis. That's just something neat to look at. It's not like a rule of thumb you need to remember or anything like that. It's just handy. So what's the domain and range here? Well, one way of saying it is the domain is all real numbers where x does not equal 0. Or we could say -∞ to 0 in union with 0 to infinity. That's our domain, and that's actually the range as well. This here is a vertical asymptote. These are never crossed. So the vertical asymptote is never ever crossed. The one that may get crossed, and I'm going to call vertical asymptote, I'm going to abbreviate it VA, because it's a lot to write every time. This line right here, our horizontal asymptote. I'm going to call HA. Sometimes can be crossed. And it's generally small values of X. Or where all the action's happening. And you'll see in a little bit. Okay. Ooh, maybe I can throw it in right here. Let's see if I can find a little clip real quick. YouTube. Tron cycle. So this is from the movie Tron. And these Tron cycles leave behind them trails of light. And the trails of light can never be crossed. Let's see what happens. I want to show you what happens. What happens when they cross. So when they get into the game area, it lets behind a trail of light. See those light walls? They act like boundaries. And if the other motorcycles hit them, they blow up. So these motorcycles will always try to approach these walls, but aim to not hit them. They treat these walls like asymptotes. See, he just crossed an asymptote. And see, now they're going, that's how a graph works. It tries to get near the line, but it doesn't cross it. You should check out Tron if you're interested, but that's what I'm going to call these things. So when we have an asymptote, like I'll do y equals 1 over x here bigger. Our x equals 0 is a vertical asymptote. And our y equals 0 is a horizontal asymptote. And both graphs cross at 1, 1 and negative 1, 1. Negative 1, negative 1. But as it's like the Tron cycle, as it gets close to the other Tron light wall, it follows it but never crosses it. That's how asymptotes work. It's like the Tron cycles. It approaches the wall, but it doesn't cross. What happens if we change the denominator slightly? Let's look at a variant. So actually, I'm going to write that down. Tron cycle. Tron cycle towards asymptotes. All right. Let's take a look at a variant. How does this change? Hold on one second. There we go. I got so many pages of notes here. I got to take pictures off of them in a little bit for you guys. You don't need that page. So let's take a look at y equals negative 1 over x minus 3. So where do we have a problem now? The denominator can never equal 0. Cannot equal 0. So let's see where the problem is. X minus 3 can't equal 0. We add 3 to both sides. X cannot equal 3. Where the denominator equals 0, there exists the vertical asymptotes. There's your vertical asymptote. So we have a vertical asymptote at x is 3. The top here can never equal 0. So the numerator can't equal 0. So we get y doesn't equal 0, and that's a horizontal asymptote. And there's a little more to finding horizontal asymptotes, especially when we've got a polynomial on top, as you'll see in a little bit. What this kind of treats it as is this is kind of like having hk equal 3, 0, and shifting our asymptotes there. Asymptotes to cross there. So y equals 0 is still an asymptote. X equaling 0 is not a problem. One, two, three, that's where we have another asymptote right here. X equals 3 is an asymptote. Now that covers a lot of it. What does that negative out front do? Well, normally the graph does this. It Tron cycles towards the asymptotes. But the negative flips it. So instead, our Tron cycles will be there and there. So this is part of it, and this is part of it. So let's expand our graphing toolbox to include this sort of information. So we've got f of x equals a polynomial function on top, p of x, over another polynomial function on bottom, q of x. When p of x equals 0, these are our x-intercepts or zeros of the graph. Zeros are roots. Where q of x equals 0, we have vertical asymptotes. sometimes a hole. And I'll show you when that pops up. It may not be like a Tron cycle effect at all. It just might be there's a hole in the graph. Now, there are other asymptotes. The horizontal asymptote is one category. The other asymptotes. We have either horizontal or oblique. Oblique is like slanted, and I'll show you that. That'll be the last one we'll show. So how do we do it? How do we find them? What we want to do is compare the degree of P of X with the degree of Q of X. And recall the degree of a polynomial is equal to the largest exponent. So f of x equals P of x over Q of x, option A. If P of x has a lower degree than Q of x, i.e. the larger exponent is on bottom. When that happens, we have a horizontal asymptote at y equals 0. Okay. The next option, they have the same degree. So f of x looks a little something like this. We have a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub 1 x plus a sub 0 divided by, let's use b on the bottom, b sub n x to the n plus b sub n minus 1 x to the n minus 1 plus, in some more terms, down to b1x and b0. So when they have the same degree, this is how we find it. Look at the leading coefficients. There will be, maybe I should do this on another page. The leading coefficients give us our horizontal asymptote. Coefficient, scratch that piece. The leading coefficients give us the location of the horizontal asymptote. And it's going to occur at y equals a sub n over b sub n. Okay. So we had the first option, the top had the smaller exponent. The next option was they have the same exponent. Our final option is if P of x is exactly 1 degree higher than Q of x. This is the scenario that leads to a slanted asymptote. Or oblique asymptote. And I'm going to reference this as OA. This oblique asymptote is a slanted asymptote, which means it's a line. It's in the form y equals mx plus b. And what we're going to do is we'll, to find it, perform synthetic division. And then the results are the coefficients of the line. After you dump the remainder. This happens like when the top is x squared, the bottom is x, has an x. Okay. Pause that and take some notes. Okay. So your job for now, let's give you some practice. For now, just find the asymptotes. F of x equals x minus 2 over x squared minus x minus 6. So pause it and try to figure out what it is based on what we said. Now, I haven't walked you through it, so you may not be able to, but see what you can reason out. Okay. So first off, what's the degree? The degree on top is 1. The degree on bottom is 2. This led to option A. For option A, we had a horizontal asymptote at y equals 0. We have a vertical asymptote where the denominator, x squared minus x minus 6 equals 0. Now, however you want to do it, quadratic formula, factoring, this factor is pretty easy. It's x minus 3 and x plus 2. And this gives us the lines x equals 3 or x equals negative 2. Here's another way to do it. And it's actually a great way to do it because you will do the following activity a lot, extreme amount in Calculus 1. Another way to find HA. Divide both numerator and denominator by x to the highest degree present. Then look at what happens what happens when x gets extremely large. Or approaches infinity. Okay. I'll assume you pause it to look at it. What I mean by that is we had, what do we have? We had f of x equals x minus 2 over x squared minus x minus 6. The highest degree is 2. So divide by x squared. Or what you're effectively doing is multiplying the top and bottom by 1 over x squared. The only reason we can do this is we're looking at what happens when x is a long ways from 0. Okay, so we're not breaking any fraction rules right here. Let's just illustrate what happens. When we distribute that, I get x over x squared minus 2 over x squared. And then I got a big denominator. I got x squared minus x minus 6. And each of these is divided by x squared. So I'm going to rewrite what that has, cleaning it up a little bit. This is 1 over x minus 2 over x squared. X squared divided by x squared is 1 minus 1 over x minus 6 over x squared. Now, what happens as x gets really large? Like, let's just look. We get 1 over 10. That's not a very big x. That's 0.1 though. If I do 1 over 100, this is 0.01. If I do 1 over 10,000, now we're getting bigger. 0.0001. As x gets large, all terms with x in the denominator go to 0. Approach 0. So that approaches 0, that approaches 0, that goes to 0, that goes to 0. Like I stopped at 10,000. What if you put in 10 billion? Now when you put it into a calculator, it's like below atomic scale. It starts getting ridiculous. The top is 0 minus 0. The bottom is 1 minus 0 is 0. So the horizontal asymptote is at y equals 0. It actually works on the next step too. And that's why I'm bringing it up. So let's take a look at another one. F of x equals 4x minus 2 over x plus 1. Here, the degree on top equals 1. The degree on bottom equals 1. They're the same, which means we focus on that portion. There's an invisible 1 right there. So our horizontal asymptote comes from there. Y equals 4 over 1, which is 4. Our vertical asymptote is where the denominator equals 0. And that gives us x equals -1. Let's take a look at that trick of dividing by the larger exponent. By a term with the highest degree. Which here equals 1, so we're going to divide by x. Each thing gets divided by x. Divide by x, divide by x, divide by x, divide by x. When we do that, we're left with 4 minus 2 over x over 1 plus 1 over x. So I'm going to rewrite that just so it shows up cleaner in the notes as I do the next step. As x approaches infinity, this goes to 0, this goes to 0, and we're left with 4 over 1, which equals 4. That's our horizontal asymptote. Ready for the final kind? Let's take a look where the numerator has a polynomial of 1 degree higher. X squared plus x over x minus 1. So I've got a degree of 2 over a degree of 1. This is going to be an oblique asymptote at y equals mx plus b. So the way we do it is we do synthetic division. Perform synthetic division. What is k here? It's the opposite sign of that thing on bottom. K equals 1 here. So I'm going to divide that into 1, 1, and 0. Because my final value is 0. There's nothing in the x to the 0 part. I bring the 1 down. I multiply by 1. I get 1. I add them. I get 2. 1 times 2 is 2, and I get 2. Synthetic division yields y equals x plus 2 plus 2 over x minus 1. Dump the remainder. There is an oblique asymptote at y equals x plus 2. Let's turn those off. We don't need those anymore. Look at that. Y equals x minus 2. I plotted as the red dashed line. X plus 2, sorry. Y equals x plus 2 is the red dashed line. And as we go towards infinity, our green line, which is our graph, approaches it in both directions. Kind of neat, right? Let's turn those back on. Because that's the oblique asymptote. What about the vertical asymptote? Where did that happen? That happens when the denominator equals 0, or at x equals 1. And we can see that right here as we get close to it. Let me turn that on. So see that? As it's approaching our asymptotes, it doesn't cross them. It Tron cycles towards them. This is a little bit different than the lecture notes I had posted. They're wrong. I didn't do the final term. I didn't put the constant in. And it was, I said y equals x, and it's not. It's y equals x plus 2. So the old notes I have are wrong. This is the correct version. So what do we do? How do we graph rational equations in general? I know it's spring break, but I'm going to keep working and making these videos for you guys. I hope to get chapter 4 knocked out in the next 2 days, and then we'll start working on what's left, getting near the end of the semester. So step 1, simplify f of x if you can. But make a note of any term or expression that you cancel from top and bottom. And the reason why I say this, these lead to bad juju numbers. Where these equal 0, it's our bad juju numbers. And they don't lead to asymptotes. These lead to holes in the graph. And you know what's messed up? When you do it in Desmos, you will never be able to see it by the naked eye. You just have to know how to find them. And I'll show you. We'll do a problem. Okay. Once we've simplified it, locate all of your asymptotes. The vertical asymptotes are never crossed. And horizontal asymptotes, oblique asymptotes can be crossed near small values of x. And when I mean small, I mean where all the action's happening, where all the bends and curves are happening. If you happen to have 1 over x minus a million, all the action starts happening near x equals a million. Areas near there will potentially be crossed. And let me make a note of that. Like 1 over x minus a million, action is near x equals 1 million. So values near there. I'm going to put p of x on top. So small values is relative. Once we've located our asymptotes, I'll pause and let you take notes. Now what do we want to do? We want to find our intercepts. We'll start off with the y-intercept. The y-intercept is where f of 0 happens so long as that does not produce a 0 on bottom. A 0 in the denominator. Denominator. Like y equals 1 over x, or f of x equals y equals 1 over x, has no 0. The only spot plugging 0 in is violates the domain. Then we'll look at our x-intercepts. What you want to do at this point, we're looking at f of x, more specifically p of x, the numerator. Where does that equal 0? Set the numerator equal to 0. Next step is often forgotten, but is important. Determine where the horizontal asymptote or oblique asymptote can be crossed, if anywhere. Sometimes they're never crossed, like y equals 1 over x. How do we do that? What we're going to do is set f of x equal to our horizontal asymptote or the oblique asymptote and solve for x. And you'll see. I'll show you. It's easier to visualize what's going on when we actually start writing it out. Finally, plot all your intercepts. Asymptotes. And note the behavior near the asymptotes. Sometimes they never cross, sometimes they cross. Sometimes picking additional values of x and finding the corresponding f of x gives more points and makes it easier. And can help. It really can. Okay. Let's take a look at a few. Let's do x minus 2 over x squared minus x minus 6. Well, I want to see if anything cancels, so I'm going to factor. The bottom factors to x minus 3 and x plus 2. Nothing simplifies. So that was part A, part 1. Step 2, find our asymptotes. And go ahead and do that real quick. Or if you remember, we actually did this already, because I'm a sneaky guy like that. I lost myself in my lecture notes. There we are. All right, so the denominator gives us our vertical asymptotes. We have a vertical asymptote at x equals 3 and x equals -2. The degree on bottom is bigger than the degree on top. This led to a horizontal asymptote at y equals 0. Or again, do that dividing by the biggest term, divide by x squared here. Three. Find the y-intercept, which is at f is 0. And I get 0 minus 2 over 0 squared minus 0 minus 6 is at 1/3. So I have a point at 0, 1/3. We find our x-intercepts. We set the top equal to 0. And we get x equals 2. So we have an x-intercept at 2, 0. Step 5 was determine if the horizontal asymptote can be crossed. So let's take a look at that. So here we set f of x equal to the horizontal asymptote. Let's solve for x. I have x minus 2 over x squared minus x minus 6 equals 0. This can only occur because that's our horizontal asymptote. Only occurs when the top is 0. X minus 2 equals 0, x equals 2. it crosses the horizontal asymptote at the x-intercept. That's not always the case, but in this problem it is. Okay. So I'm just going to put all that together on one page, the important stuff, and then we'll graph it. So asymptotes. Vertical asymptotes were at x equals 3 and -2. Horizontal asymptote was at y equals 0, and it's crossed at x equals 2. Our intercepts were 0, 1/3, and 2, 0. Let's just get that set up. X equals 0 was never a problem, so the y-axis stays solid. Y equals 0, or the x-axis, is an asymptote. So that's my x, that's my y. Okay, what else do we have here? So our vertical asymptotes are at x equals 3. And x equals -2. So our asymptotes are in red. Now we plot our intercepts. 0, 1/3 is about there. 2, 0 is right there. Now I know these two have to connect. And since they're connecting like that, this has no choice but to Tron cycle downwards. And this has no choice but to Tron cycle upwards. What about this region and this region? Well, the easiest way to do it is it's going to be on one side of the asymptote. It's either above the asymptote, above HA, or below. So pick some X. Let's go with, this is x equals 3. X equals 5 is right here. What is f of 5? We have, recall, let me rewrite the equation. F of x was x minus 2 over x squared minus x minus 6. I've got 5 minus 2 over 5 squared minus 5 minus 6. This is 3 on top. 5 squared is 25. Minus 5 is 20. Minus 6 is 14. F of 5 equals 3/14, which is above oops, God, that's going to make my graph look bad. Above HA, which means we have this. It's got to go like that towards that asymptote, and it's got to go like that towards that asymptote. Generally, it's on the opposite side for the other region, but let's just pick a region over here. Let's do like f of -4. I've got -4 minus 2 over -4 squared minus -4 minus 6. I get -6 on top. -4 squared is 16, positive 16. Minus -4 is add 4. 16 plus 4 is 20. 20 minus 6 is 14. F of -4 is a negative value. Is less than 0. So it's going to be below y equals 0, and it's got a Tron cycle here. And that's the graph of that function. Look. Neat, huh? All right, let's try another one. We're going to do this one right here. And I'm going to pause and I'm going to let you guys try. Well, I'm going to pause. When I say I'm going to pause, hopefully you're going to hit pause, because I don't want to just sit here for 15 minutes and stare at the camera and make pretty faces. So find your asymptotes, find your intercepts, see if your horizontal asymptote can be crossed, and try to plot this. Okay. If you recall, we did this setup earlier too. We found the vertical asymptote is where the denominator equals 0, x equals -1. The horizontal asymptote, I can look at the coefficients of the leading two because they have the same degree, and we get y equals 4. Our intercepts, the y-intercept is when f evaluated at 0, which is -2/1. I have a y-intercept at 0, -2. The x-intercept is where the numerator equals 0. We get x equals 2/4, which is 1/2. The x-intercept is at 1/2, 0. Can we cross HA? We're going to take f of x for x plus 1, and we're going to set it equal to the horizontal asymptote. Multiply both sides by x plus 4. We get 4x minus 2 equals 4 times x plus 4. We distribute. When we try to solve this equation, we subtract 4x from both sides. We get -2 equals, I said x plus 4, that's x plus 1. That's x plus 1. That should be 4. I get -2 equals 4, which is false. It doesn't cross HA. So my asymptotes, neither of them are on the axes. So here's my x and my y. I have a horizontal asymptote at y equals 4. And I have a vertical asymptote at x equals -1. I have a y-intercept at 0, -2. And I have an x-intercept at 1/2, 0. So those are my intercepts. They must connect, and they can't get near the wall. Or, well, they can't cross the wall, so they Tron cycle towards the asymptotes. Let's take a look at what happens over here. Like f of -2 is to the left. And what we're really looking to see is f of -2 less than or greater than the asymptote, the horizontal asymptote, 4. So what is f of -2? It's 4 times -2 minus 2 over -2 plus 1. This is -10 over -1. F of -2 equals 10. It's greater than 4, so it's gonna be above that horizontal asymptote. In fact, it's way up there. Sure enough, we've got an asymptote at y equals 4. And x equals -1. See that? So we did it right. And x equals -1 or -2 did cross at 10. If I can get the cursor right on it, there we go. Okay. Let's try another fun one. There it is right there. Let's do this one right here. (2x² plus 3x minus 4 over x² plus 6x plus 9. Pause and work these out. Okay, I'm going to assume you did. The denominator gives us our vertical asymptote. This factors to x plus 3 squared equals 0. So x equals -3 is a vertical asymptote. That black pen is dying. The horizontal asymptote they have the same degree, top and bottom, so it's the leading coefficients. Y equals 2 over 1 or y equals 2. Now let's look for our intercepts. The y-intercept is at f of 0 equals -4 over 9. So 0, -4/9 is a point on our graph. The x-intercept is where the numerator equals 0. I don't think that factors, so I'm going to do x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a. Bottom is 6 here, or 4. I've got 9, and then -4 times 2 is -8, times -4 is +32. 9 plus 32 is what's going on inside, is 41. Now, that's not all that helpful. You throw it into a calculator. I get approximately 0.85, 0, and -2.35, 0. So those are valuable points. Now we have to ask, does this cross the HA? And we do that by setting it equal to HA. If I multiply both sides by the denominator, 2x squared plus 3x minus 4 equals 2 times x squared plus 6x plus 9. We'll distribute. Looks like the x squareds go away. That's nice. Maybe since those are gone, I'm going to move my x's so that I have a positive coefficient. I'll move the x's to the right side, which means I'll move my numbers to the left. I get -22 equals 9x. So x equals -22 over 9. This is approximately -2.44. And this is at where it crosses the HA. Which gives us our y value, y equals 2. So we have a point at -2.44, 2 is on the graph. I'll let you soak that up. Let's take a look at plotting it. So our axis, x-axis and y-axis, are not asymptotes. I can graph them like normal. I have a vertical asymptote at x equals -3. I have a horizontal asymptote at x equals 2 or y equals 2. And where were my points? I've got 0, -4/9, which is below the x-axis. That's a point on the graph. And I've got 0.85. It's right about there. Negative 2.35 is right about there. So those are my x-intercepts, my y-intercept. And we cross the horizontal asymptote at negative 2.44, which is right about there. Which means if we connect the dots, it must go down a little bit maybe and come up like this. And over here, it does this. The Tron cycles towards the asymptotes. What about on the left? So we had negative 10 is easy to work with. I don't really have to do a lot of work. It's easier to do the work, let's say that. Negative 10 squared is 100. I've got 2 times 100 is 200. 3 times negative 10 is minus 30, minus 4. Over negative 10 squared is 100. 6 times negative 10 is negative 60. I should say plus 9 on the bottom. Plus 9. So 200 minus 30 is 170, minus 4 is 166. Over 100 minus 60 is 40, plus 9 is 49. I need to know, is that greater than 2? Which is my HA. Well, this value is approximately 3.38. So it is greater than, which means we're gonna be above HA. Which means we'll be Tron cycling towards the walls over here. So I had x equals negative 3, y equals 2. Turn on our asymptotes, turn on our graph. And lo and behold, what we drew. Looks like I could have made it spike down a little bit more right here, but again, since we haven't identified how to find the turning points, other than plugging in a whole lot of values, it seems kind of pointless. Just sketch it right now. Okay. Our next problem that we're going to take a look at. Let's look at, it's on the screen, x squared plus x over x minus 1. And I think I showed that to you earlier. So earlier we found the vertical asymptote was at x equals 1. And we used synthetic division to find our oblique asymptote, which is y equals x plus 2. What are the intercepts? Y-intercept is at f of 0 is 0 over negative 1, which is 0. So the y-intercept is 0, 0. The x-intercept is where the numerator equals 0. That factors into x times x plus 1. And we get x equals 0 or x equals negative 1. We've already got the 0 one. The only new one we have is negative 1 comma 0. That happens to be an intercept as well for x. Okay. Does this cross the oblique asymptote? Set f of x equal to the oblique asymptote. X squared plus x times x minus 1 equals x plus 2. So I get x squared plus x equals x plus 2 times x minus 1 when I clear fractions. If you distribute, we've got x squared minus x plus 2x minus 2, x squared plus x minus 2. We subtract, we get 0 equals negative 2. Does it cross the oblique asymptote? No. It does not cross OA because this is false. Now I've already got it sketched up on Desmos. Let's just use what we have here to plot it. X and Y. So the vertical asymptote is at x equals 1. Y equals x plus 2 crosses at 0, 2, and has a slope of 1. We have intercepts at 0, 0, and negative 1, 0. Now we know as it goes towards the asymptotes, it's got to go like that. And that's got to go like that, which means it's coming up just a little bit right there and crossing. What about to the right? Let's check f of 2. Two squared plus 2 over 2 minus 1. F of 2 equals 6. Is that above y equals x plus 2? The oblique asymptote. Plug in 2 here. On the oblique asymptote, we have the point 2 comma 4. As you can see right there, 2 comma 4 is there. Our line has a point at 2 comma 6, which means it's above. Which means it's got a Tron cycle there. Now where the turning point is, I'm not sure. But that's the good stuff right there. One more problem. Let's look at this one right here. F of x equals x squared minus x minus 6 over x minus 3. First off, we try to simplify. The top factors into x minus 3 times x plus 2. The bottom is x minus 3. Those x minus 3's cancel out. F of x looks identical to x plus 2. But since we canceled out x minus 3, there is a hole at x equals 3, which would be f of 3 is 5. So there's a hole. 3 comma 5 is a gap. So 3 comma 5, 1, 2, 3, 4, 5. There's a hole right here. We know x plus 2 crosses right there, and it has a slope of 1. There's a hole or gap. Look what happens on Desmos. Does it look like there's a hole there? 3x equals 3 is right here. It looks like the line keeps going, right? It doesn't matter how close I get to this point either. I zoom in all the way as much as I can. Doesn't matter. But watch what happens if I slide the line to it. It says 3 comma undefined. It will tell you there's a hole if you highlight it. But if you're not clicking on it, you can't possibly zoom in enough that it's going to show you a hole. Okay? So you cannot rely on graphing technology for everything. All right? That's it. So, yeah, let's make a note of that. The hole only appears on Desmos if you click on the line at x equals 3. And the only way you're going to know that is to understand how the function works. Graphing technology won't do everything for you. Is not the be all end all. You're gonna have to learn some math. Going to have to learn this stuff. Or every time you graph something on Desmos, you can try to slide your thing across it at a very, very slow pace. And hope you have to zoom in really closely. Because notice when I'm zoomed out this far, trying to hit 3 comma 5, a little hard. It's so easy to go past it. You gotta go so slow. There we go. when I zoomed in, it was really easy to do. All right, that closes out 3.5. This is the end of chapter 3. There is a section in 3.6 if you actually want to look at it. It's called, what was it called? Variation. And we're not going to work on it. So I'll turn that off. And we will call this an end. Peace.